Okay, this is a quick video on B1 and B2 for trigonometry in grade 12. All right, so you need to be able to convert between radians and degrees. All right, so here we have 74 degrees, and we know to convert, we can just multiply it by our conversion, which is pi over 180. I always remember which one goes on top by 180 degrees, and I want the degrees to cancel. So if one's on top, one's on the bottom, they'll cancel out. And there's two ways we can write this. We can write it in terms of pi, so it's like 74. Whoops. So it's like 74 pi over 180, and you just reduce that to lowest terms. So there's that way. Or you can actually just use pi, so 74 times 3.14 divided by 180, and we can write it as a decimal, so 1.29. So I would specify, please write your answer rounded to 2 decimal places, or please write it in terms of pi. So this would be 1.29 radians. And then 150 degrees, if I wanted to convert that to radians, I just multiply it by the same conversion. But let's say I want to leave this one in terms of pi, because it looks like it's going to work out a lot nicer. So 150 pi over 180. So now I simply take these guys right here and reduce them to lowest terms, which would be
25 30.
Okay, so we can reduce that to 5 pi over 6, and shortcut way to do this would be pi over 6 is one of our special triangles, guys, which is actually 30 degrees, and 5 times 30 degrees is 150, so that's just like a quick conversion. Okay, so then we could write, so this would be writing it in terms of pi, and this would be writing it as a decimal. So I would specify which one you had to do. Okay, and then there's the opposite, so where you have to convert radians to degrees. And in this case, I personally just sub the pi out for 180, or another way to think about it is multiply by 180 over pi to convert to degrees, so these pi's cancel out. So I just get 2 times 180 divided by 3. So 360 divided by 3, which would be 120, I believe. Okay, and then if you have a decimal, like 1.23, same conversion, so times 180 over pi, but now there's no pi's to cancel out, so you just straight up multiply. 1.23 times 180 divided by 3.14, and I do not have a calculator, so I can't do that in my head. But yeah, you just punch that into your calculator, and it's, I don't know. Okay, moving on. Primary and reciprocal trig ratios. So this is all your special triangle stuff. So things you should know for the quiz are, you should know your 2 special triangles. So you got pi over 3 and pi over 6 as your angles. So this side would be root 3, this side would be 1, and this side would be 2. So you have to kind of remember which side goes with which. I always like to remember, so here's my other special triangle, pi over 4, pi over 4. I like to remember that the hypotenuse is always 2, and 1's a root 2. This guy has side lengths of 1. It's an isosceles triangle, so it has to have the same 2 sides. And this guy, I like to remember that like pi over 3 is right across from root 3. So it's kind of have some system, and then you can just reproduce these. And as soon as you get your test, I would just write those down so you have them. Okay, so then we just have to apply those to 360 degrees, or 2 pi. So here we have our grid. So it goes from 0 to pi over 2, which is 90, pi, which is 180, 3 pi over 2, which is 270, and then back to 2 pi. All right, so we've got our initial arm always lies here. And then let's say I wanted you to find the primary and reciprocal trig ratios of 7 pi over 6. So first I would just determine, where does 7 pi over 6 go? Quadrant 1, 2, 3, or 4? So it goes in quadrant 3 because it's less than 3 pi over 2, but bigger than pi. Then I always connect it to the x-axis. So now I know this angle right here is 7 pi over 6. And I know my related angle right here would be pi over 6. So then this side would be pi over 3. And if I had to label my sides, I just use this special triangle here. So I know this side would be negative root 3, this side would be negative 1, and this side would be 2. Okay, so next step is I have to say what my primary and reciprocal trig ratios are of 7 pi over 6. So starting with sine of 7 pi over 6, just recalling my cast rule too. Since I'm in quadrant 3, only tan will be positive or cotangent. Okay, so 7 pi over 6 is going to be negative, and that makes sense because if you check it out, we use our related angle of pi over 6, and our opposite side is negative 1, and our hypotenuse is 2. So I've got negative 1. Yeah, I'm not going to use yellow. Okay. Negative 1 over 2 for sine. Then I move on to cos of 7 pi over 6. And cos of 7 pi over 6 is adjacent over hypotenuse, so negative root 3 over 2. And then tan should be my positive one. And that's opposite over adjacent, so negative 1 divided by negative root 3, which is just positive 1 over root 3. And then I always want to rationalize my denominator. So I'm going to multiply the top and bottom by root 3. So I get root 3 over 3. So those are my primary trig ratios, sine, cos, and tan. And if it asks me to, I could also find my reciprocal ones. So I have cosecant of 7 pi over 6 is, I just flip sine, so it would be negative 2 over 1. I have secant of 7 pi over 6 is 2 over negative root 3. Then I have to multiply top and bottom by root 3, so I get negative 2 root 3 over 3. And finally cotangent, which I can't seem to fit on this page. Okay, so cotangent 7 pi over 6 is equal to the opposite of tan. I'm going to steal this tan one. So I get root 3 over 1. Cool, so those are my 6 ratios. And I got them all by just using this related angle and just SOHCAHTOA. That's pretty much it. So yeah, you can expect to get on the test some kind of angle that's going to be somewhere between 0 and 2 pi. And you'll first have to figure out like, oh, where does that angle belong? So is it here? Is that my angle? And then I connect it, and then I figure out which special triangle I use. So yeah. Okay, and then we can extend this idea to like clocks or the Earth's rotation or something, I don't know. So let's say we're extending it to a clock, like on the practice quiz. So you're just pretending that let's just give ourselves a clock. That's horrible. And I'm going to make my clock the weirdest clock ever, and I'm going to say that, just so it fits with my unit circle, I'm just going to say this is 12 o'clock or 0 o'clock, and then like this is 3 o'clock, this is 6 o'clock, 9 o'clock, and back to 12. So like it's a bit of a sideways clock and backwards, but I'm just relating it to trig. So then if I have my initial arm starting at 0 or 12, let's say I wanted to figure out how many, the angle the hour hand travels in like 5 hours. So what kind of angle is it traveling? So it's starting here, 12 o'clock, then it's going like 1, 2, 3, 4, 5, and it gets almost to 6 o'clock, but not quite. So that would be my clock in standard position. So it looks a bit ridiculous, but That would be like 5 o'clock. So I want to figure out, oh, how many angles did that travel? Or how many radians? Okay, so normally we would have represented this as 0, or 2 pi. Like a full rotation's normally 2 pi, but now we're saying it's 12 hours. So I like to write that as a ratio. So I like to say 2 pi is actually 12 hours now. So I've just wrote them as a ratio together. They represent the same thing, a full rotation. But I don't want a full rotation. I actually just want to know what happens at 5 o'clock. Like how many radians is that? So I want to change my 12 into a 5. So I have to figure out, what would the equivalent ratio be? So I just need to isolate x. So I'm just going to multiply both sides by 5. So if I multiply this by 5, they cancel. And then I just have to multiply that by 5. So I get 10 pi over 12. And if I reduce that to lowest terms, I get 5 pi over 6. So it turns out in 5 hours on a clock, the hour hand would travel 5 pi over 6 radians. Or alternatively, you could calculate this a totally different way. You could figure out how long 1 hour is. So you know that 12 hours is 2 pi. So why don't you just maybe divide 2 pi by 12? So if I'm going to say, well, I want to divide 2 pi by 12 and like legit divide it, then I know pi over 6 is how far 1 hour is. So if I want to go 5 hours, I just multiply pi over 6 by 5 and I get 5 pi over 6. So you just have to kind of like whatever situation is. This one happens to be a clock. I gave you another one that was like the Earth's. I can't remember what it was. But you just have to make it fit with whatever item they give you and always relate it back to this, like a full rotation being 2 pi. I know 6 hours would just be pi. I know 9 hours would be 3 pi over 2. And I know 3 hours would be pi over 2. So they still relate back to our normal radians. Okay, arc length. We touched on this when we did the bike rim. So arc length, and we also did like a carousel, like a unicorn on a carousel thing. So here you have a circle. Here's the center of your circle. You've got this thing right here, which is your radius. And then you can make a terminal arm, so another radius. And the angle formed in between these two radiuses is theta. And then this guy right here is the actual arc length, which we represented as S. So we made an equation that said S is equal to theta times R. So you can calculate the arc length by doing the radius times the angle, which might be helpful. So we talked about like, oh, this is a carousel, like a bird's eye view of a carousel, and you're riding a horse, and you want to figure out the distance your horse traveled in this circle, if it made it, a certain amount of radians around. So you might want to use that to figure out like the distance traveled. So you can get any part of this information you can figure out any one of these unknowns. So the question on the practice test gave you the radius of the circle. It said the radius was 75 centimeters and that the angle was 2.3 radians. So the angle is 2.31 radians, and it wanted you to determine the arc length. So all you had to do was plug in the numbers, 2.31 times 75, and your arc length ended up being 173.25 centimeters, which is just how far you traveled around the outside of the circle. Okay, that's it for B1, and finally B2, just a couple things on B2. The basic sine and coast graphs. So you should know that sine x, and if you don't know, you can just stick it in your calculator and figure it out. Sine x, I always say starts at 0, 0, 0, but it doesn't actually start anywhere, but it's got a point at 0, 0 anyways. It's got a max value of 1 and a min of -1, and it's got a period of 2 pi. So So some key points here would be pi over 2, pi, 3 pi over 2, and 2 pi. Just like those on the unit circle. So then what sine does is at 1 it has a value of pi over 2, and then 0, then -1, and back to 0. So that's what your sine curve looks like. And obviously it keeps going in both directions. So our sine curve has a period, meaning it goes through one cycle before it starts repeating again. It has a period of 2 pi. It also has an amplitude of 1. So that's our amplitude. And our amplitude is the distance from the middle of the graph. So here's the middle of the graph to the max, or the middle of the graph to the minimum. It's the same distance, and our amplitude here is 1. Then we've also got this line right here, which we call the equation of axis, and that just splits our graph right in half. And the equation of our axis in this one is y equals 0. So those are like our three main key features: our period, our amplitude, and our equation of axis. And that holds true for sine x and cos x. The only difference for cos x is that it passes through this point up here, 0, 1. And then when it does this, it follows the same pattern. So it goes down here, and then down to -1, and back up, and then it keeps going. So it still has a period of 2 pi. It still has an amplitude of 1. And it still has an equation of axis right through the middle at y equals 0. So that's what your sine and cos graphs look like. Okay, then if you have to describe a transformation or create one or graph one, let's just quickly sum up K, A, D, and C, and then we're done. Okay, so here's our A value. So that's saying our amplitude is 2. So that's the difference from the equation of axis to the max. This guy affects our period. So they say normally the period of a sine curve, normally the period is 2 pi. But this guy, since it's a half in the K value spot, that's K. Since it's a half, it means our sine curve is going to occur half as many times as normal. So it's actually going to take longer. The period's going to be longer. Because if you normally go through 1 and 2 pi, now you're only going to get through half of 1. So now you're going to just get halfway, and you're still going to need to go the other halfway. So if you just follow this logic, period is 2 pi divided by k, you can get your period pretty quick. So 2 pi divided by a half is the same thing as actually multiplying by 2. So 2 pi divided by a half is actually 4 pi. So our period is actually 4 pi. This guy right here is a phase shift. So we have a phase shift. So our graph is actually going to go left pi over 2 radians. So the whole graph is going to shift left. And then this guy right here is going to shift our whole graph down 1. Okay, so let's say we had to graph it, because that's the least fun part. Okay, I'm just going to shift that up. Okay, graph it, then we're done. Okay, cool. So scratch that. Start here. So usually we'll give you an interval in which to graph it. We'll say like, graph it from 0 to 2 pi or from 0 to 4 pi. I think it's important that you at least graph one full period of your function. So I'm going to graph mine all the way to 4 pi. Okay, so first I'm going to figure out where's my equation of axis. So since I've got this -1 here, this guy tells me the equation of axis is at y equals -1. So might as well just plot that on. Okay, so y equals -1 is going to be our equation of axis. So I'm going to put that in yellow. So I know that's like the midline of my graph. Then I know my amplitude is 2. So that means from my equation of axis, the tallest my graph is going to get, I'm just going to stick that in red. The tallest my graph will get is up here at 1. So I know my max will be this line here. My max. And I'll go 2 down from there, so I'll be at -3. So this, not that you need to put a dotted line, I'm just doing this for the explanation. So that's my min. Okay, cool. So I know my graph's going to occur like within this interval. Okay, here we go. Now I know my period's going to be 4 pi. So I think what I'm going to do is I'm just going to stick my scale on now. Or there's the whole philosophy of like moving your y-axis around. It's totally cool too. Okay, so I'm going to sketch out a pi over 2, pi, 3 pi over 2, 2 pi, what comes next? What's 2 pi plus pi over 2? 5 pi over 2? No. Yeah? It's really late and I'm crazy. 4 pi over 2? 5 pi over 2? That seem right. 3 pi? I don't know. I hope that's right. 7 pi over 2 maybe? And then 4 pi?
5 pi over 2.
I did 5 pi over 2. And then 3 pi and then 7 pi over 2. That's totally right. Okay, cool. I'm pretty sure. Okay, so I made a scale. Now I'm just going to plot some points. Okay, so normally sine curve starts at 0, 0. But mine's going to be down to -1 here. Because that's where the middle of my graph is. But I also have a phase shift of left pi over 2. Sweet. Make a negative pi over 2 here. Okay, so I think instead of starting at 0, now my graph's going to start back here. Okay, then my next point was going to be, if I didn't have this phase shift, was going to be at my max of like pi over 2 and 1. But now my graph, like it would have been here if I didn't have a phase shift, but I have to shift mine back pi over 2, like left. So now it would be here. So now I can pretty much just gauge what my pattern's going to be. So I know I'm like pi over 2 is kind of my next line over, and then I'm just going between the yellow lines and the red lines. So my next step would be like here, then I'd be down at the red line, then back up at the yellow line, and then the red line, and then the yellow line, and then the red line, and then the yellow line, and the red line. So I just like use my pattern to kind of graph it. Oh, you know what? I messed that up. Yep. Yes, I did. Because I totally blanked on my period. Period's 4 pi. That means it takes 4 pi to complete one cycle. So what am I talking about? This is crazy. It's hard having a K and a phase shift. Just saying. Okay, I got this. Okay, I'm going back to Seb's way. Okay, I think. You know what? All right, I'm going to pretend I don't have a phase shift for a sec. So I got my graph here at -1. And then normally, okay, so I know I have to complete a cycle in 4 pi. So I'm going to be like back to here in 4 pi. So then the middle of my cycle would be at 2 pi. That's where I have to get midway. And that way midway between there is pi, which will be at the red line, and midway between these two is 3 pi. Okay, cool. I feel good about that. Whew. So that's my normal sine curve, like that. Cool. So that's like one period in 4 pi. That looks awesome. But then unfortunately, I have a phase shift left pi over 2. So So I have to take all those blue points and shift them left. Or, using sub strategy, I could take my whole y-axis and like shift it to the right pi over 2, which is kind of cool. But then I have to relabel my whole axis, which is fine too. Or I could just take all those points and shift them left. So whatever you want to do. I feel like this is not a helpful video anymore. Okay, I'm just going to shift my points left. Okay, so my green line is actually my graph. Cool, and I can just erase my blue line. But not actually, because it seems like that's actually really annoying to erase. Oh, kind of erasing it. There we go. Okay, cool, so that's my graph. So, okay, a phase shift and a period change is super annoying, but you could just go slow, graph one, like, you know what, graph one at a time. Like, pretend you don't have a phase shift, graph it out, and then just shift everything left or right. That's not the worst. Or draw your scale on after. I don't know, get a strategy, play around with it, and good luck.